formula, and depending on the information that you may have temperature, you may not have wind data. So you will get an empirical formula for computing evapotranspiration based on temperature only. You may have wind data, so get a more complicated one, which accounts for wind also. So select your formula depending on your information and get an estimate for EP, depending on time, of course, because meteorology is time varying. And once that you have the estimate of EP, we now assume that the effective evapotranspiration, the one that you actually have, which also depends on water availability, is linearly related to the potential evapotranspiration through the soil water content. It means that when your storage in the catchment is 0, you don't have any actual evapotranspiration. When your catchment is saturated, you have actual evapotranspiration, which is the same as potential evapotranspiration, and in between you have a linear change. This is a scheme that is adopted by several models. And therefore it becomes easy, once that you have your estimate for WT, it becomes easy to compute ET, and then you can update WT by subtracting ET here. I think here I have to make a change here because this is ET, not EP, unless I am missing something. Let me see. I don't think so. Yeah. I need to make a change here. Okay, this is ET. So there are two changes that I have to make. One at the picture. And by the way, if you notice mistakes, as I told you, I'm writing these web pages while I progress with the course. If you notice any mistake, I'm very grateful to you if you send me an email so that I can correct it. Okay, so I think we are done. The only thing, of course, we need to write a code at this stage. And there is one other thing that I wanted to tell you. Yes, okay. So, of course, we are working, as you see, in a finite difference scheme. So I am adding rainfall. After having added rainfall, I compute storage and contribution to river flow, and then I compute evapotranspiration, and I subtract evapotranspiration from storage. This is not an analytical scheme. I don't have an analytical formula that, depending on rainfall, gives me directly contribution to runoff and storage and contribution to evapotranspiration. I need to apply a numerical scheme. So I get the rainfall data, I increase storage, I subtract evapotranspiration, and then I move forward with the next time step. So this will be a numerical scheme. It's not an analytical scheme. And of course, in a numerical scheme, you get different solutions depending on the order that you follow in subtracting, for instance, evapotranspiration. So you may decide to compute the surface runoff and then subtract the evapotranspiration, or you may decide to first subtract the evapotranspiration and then compute the surface runoff. The result is more or less the same if your time step is very fine. So if you work with a time step of 1 second, of course you don't have important changes in contribution to runoff and storage at each time step, and therefore it doesn't matter whether you follow an order of numerical operation rather than another one. If you work with monthly time steps, of course it becomes important if you subtract evapotranspiration before computing runoff or the other way around. These are the usual approximation induced by numerical computation. Actually, we assume that it doesn't matter, so the scheme that I will propose to you will first compute the runoff and then subtract evapotranspiration. But of course, you may decide to change the order. We are moving within the limits and the boundaries of numerical approximation, but still the scheme is stable. This is a stable scheme, so it doesn't give rise to instability. It can be proved that it's stable, provided that you put the checks, no negative values for storage, no negative values for contribution to surface runoff, and then the scheme is stable. I didn't finish because the model has an appendix, but let's stop for 15 minutes.